Well, we're going to start Chapter 2 on differentiation, Section 2.1, the derivative and the tangent line problem. At the very beginning of the course, there was a section that talked about how pre-calculus developed into calculus using the idea of the limit. But even before that, we talked about two classic problems in calculus to describe the two branches of calculus, which is differential calculus and integral calculus. And that's what we're getting to today, the idea of the tangent line problem, which we discussed in a previous video. Now, what does it mean, though, that if a line is tangent to a curve? Now, we know what it means when it's tangent to a curve like a circle, because if you draw the radius to the point of tangency, it's perpendicular to that line. But here I have what looks like a little bit like a parabola, and I have a line that is tangent at point P. At least I try to draw it so that it appears to be tangent. But that we understand. I think we have a pretty good concept of. But what happens if we have a curve that looks a little bit more like the one in the middle? See, it still has the single point of intersection, but it's the line is not on the outside or above or below the curve. It's partly above, partly below. It passes through. This point being where the curve kind of changes from being curved downward to curve upward. We call this actually a point of inflection. And then we have the third possibility where we have the idea that's similar to what we have in the first example here, where we have our tangent line to the point P here, but because of the way the curve is drawn, the line actually intersects it in more than one place. Is that considered a tangent line? So we're going to have to kind of define what we mean here with tangent lines to a curve. So to determine the slope of a tangent line using first an approximation, and then we'll use the limit to find the exact value, we find the slope of a secant line. And the secant line here is in red. It's a line PQ here. Notice here at this point here, point P, my x value is c. My function is y equals f of x, so I have the point c f of c. And then I go a little bit bigger than c by, let's call it, say, delta x. So this, typically it's a small positive number. So this is a little bit bigger than c. Now I drew it so it looks like it's quite a bit bigger than c to make the diagram look a little bit easier to understand. But what I have here is I have point Q, which is the point c plus delta x, f of c plus delta x. And if I draw this red line here, it's not a tangent line, it is a secant line. And the secant line here, PQ. Now I can find the slope of a secant line because I have 2 points. I have this point P and point Q here, so that's what I'm going to do. I'm going to take f of c plus delta x minus f of c over c plus delta x minus c. Now you can, in the bottom here, these c's are going to cancel, and I end up with this expression, which we know as the difference quotient expression, except typically we have an x here instead of a particular value c, but that's because we're looking at a particular point here. So as delta x goes to 0, as this distance here gets smaller, so this point, that means this point Q comes over here now. And if point Q is over there now, then what happens? Oh, here, I've got a green pencil. Is that my graph, the secant line, if I can draw this worth a darn, has changed a little bit. It, in this case, because of the way my function is drawn as an increasing function, it looks like the slope of the green line is a little bit smaller than the slope of the red line. Now if I move point Q, call this Q1, if I move point Q, let's say way over here, call it Q2, you're going to discover, and I don't think I have another colored pencil. Oh, I got a red one. Take that back. I got a red pencil right here. So let's draw this one in if I can. And you can see that the line has changed again and that the slope of the line has changed again. Now I'm going to find the equation of the secant of this tangent line. And by using these secant lines, and notice here that my graph doesn't, of course, not the best drawn graph, but it looks like that this third secant line that I've drawn in here in red appears almost to be tangent at this point. Now it's because point Q, I call it Q2, is getting closer and closer to point P, because that means that this is going to 0. There's that limit idea again. So as delta x goes to 0, point Q approaches point P, which means that the slope of the secant line is approaching the slope of the tangent line. Okay, and that's where we're going with this definition right here. A tangent line with slope m. If f is defined, let me move this up just a little bit here. There we go. If f is defined on an open interval containing c, and the limit is delta x goes to 0, in the change in the y values over the change in the x values, which is our difference quotient expression, the limit is delta x goes to 0, of f of c plus delta x minus f of c over delta x is equal to m. If this exists, then the line passing through this point, the point of tangency with slope m, is the tangent line to the curve at the point c f of c. So we already are going to be given enough information to find this value here. We just need the slope, and then we can find the equation of the tangent line. The slope of the tangent line to the curve is also called the slope of the graph, or the slope of the curve, f at x equals c. Now I know that sounds a little weird. Slope of a line is easy because it's constant, but the slope of a graph of f, or the slope of a curve, it's going to change based on what point of the curve you're looking at, what value of c. All right, so let's try one or two. Let's find the slope of f of x equals x squared minus 2x at the point 3, 3. Now, to do this, I have to take the limit, because I have the point. I need the slope here. Well, they're just asking for the slope. I don't even need to write the equation of the line, but I'm going to find the slope. It's going to be the limit as delta x goes to 0 of f of, now here's my c value, that's the x value of the point, f of 3 plus delta x minus f of 3 all over to delta x. Yeah, I think you can read that all right. So this is the limit. Got a little algebra to do here. As delta x goes to 0 of, now I'm going to substitute all this in for x up here. So I have 3 plus delta x squared minus 2 times the quantity 3 plus delta x minus f of 3. F of 3 is what I get when I plug 3 in, which looks like 9 minus 6, which is 3, all over delta x. Now, if you start looking at this as a limit and you're trying to evaluate this with direct substitution, you're going to get 0 over 0. So that's not going to help you. You're going to have to do a little bit of algebra and see if we can figure this out analytically. This is the limit as delta x goes to 0 of, this is going to be 9 plus 6 times delta x plus delta x squared. Here I have to distribute. I squared this, so I'm going to get minus 6 minus 2 times delta x minus 3 all over delta x. Lots of algebra. Be careful and don't skip steps. Now I can see here that I have a 9, a minus 6, and a minus 3. They're all going to cancel out. That's just 0. And I have like terms here. I have a 6 delta x and a minus 2 delta x. So that's going to be the limit as delta x goes to 0. By the way, I didn't really emphasize this probably as much as I should have in the chapter 1 on limits. But until you actually evaluate and make the substitution, you need to write the expression for the limit in each time. So this is going to be 4 times delta x plus, looks like, delta x squared all over delta x. Now I can factor a delta x in the numerator. I get the limit as delta x goes to 0. If I factor out a delta x here, I have 4 plus delta x all over delta x. Now you see why I went through the hassle of doing all this simplification, because now the delta x's cancel, and that's what was giving me 0 over 0. So now I have the limit as delta x goes to 0 of the expression 4 plus delta x. Well, that's 4. If this is going to go to 0, then I'm going to have 4. And that turns out to be the slope of the tangent line to this curve at this point. It's pretty straightforward stuff. Okay? Now, just a lot of algebra. Be careful. One little slip up, one sign, and there it goes. The heck in a handbag. All right, next guy up. This one's a little simpler, and this one should be a little bit more obvious, because my curve here is a line, and the slope of my line, it's already in slope-intercept form, is 3. So it doesn't matter what point on the curve, my slope better be 3, because the tangent line drawn to a line is actually the line itself. It should have slope 3. Let's see if we get that. So this is my C here. I'm going to let m is equal to the limit as delta x goes to 0 of, this would be f, or actually in this case my function's g. This is going to be g of -2 plus delta x minus g of -2 all over delta x. So I go right to the definition. This is the limit as delta x goes to 0. I'm going to plug all of this in right there for x. So I have 3 times the quantity -2 plus delta x minus 5. That's all this. Minus g of -2. If I plug a -2 in there, I'm going to get -11, what I expected. So minus a -11 all over delta x. So let's see what happens here. Got to simplify this. This is the limit as delta x goes to 0 of, up top, I have -6 plus 3 delta x minus 5, looks like plus 11, all over delta x. Well, -6 and -5 and a positive 11, that's 0. So I get the limit as delta x goes to 0 of 3 times delta x, let me put parentheses around that, times delta x, and of course these are going to cancel, so I have the limit as delta x goes to 0 of 3, which is 3, which is what I suggested earlier on, because this is a line and it has slope 3. Now the definition of the tangent line to a curve does not actually cover, because it says that the limit exists, does not actually cover the possibility of a vertical tangent line. So if you have a function that's continuous and you end up with a vertical tangent line, then what ends up happening is when you go through this process of taking the definition of finding the tangent, the slope of the tangent line, you're going to get positive or negative infinity. That's going to tell you that the slope is undefined, or if you'd like to think of it in more of a calculus manner, that the slope is infinite, and that you would have a vertical line there. Now, this expression that we had in the definition, this expression right here, pops up quite a bit in calculus, and they gave it a name, and they called it the derivative. The derivative of f at x is given by, now this is the notation, this is a little prime symbol, it's kind of like an accent mark here. F prime of x is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x, provided the limit exists. Now notice it doesn't have a c in here because we're looking at this for any value of x that the function is defined for. So when we have this, if for all values of x the limit exists, then we say that f prime, or the derivative of the function f, is a function of x. So we actually get a new function. It's just called the derivative. The derivative of a function is kind of like a slope finding machine. It gives you the slope of the tangent line at the point x f of x, provided that the graph has a tangent line at this point. So if you can find the derivative, and then you say, well, I'd like to find the slope of the tangent line at the point 2, 3, well, you could just, since it's a function of x, you just plug 2 in for x into the derivative, and you would have it. Convenient. Now, a little vocabulary here. We have the derivative of a function. The derivative of a function is, when we find the derivative, we sometimes say that we're deriving, but we also use the expression differentiate. This is a verb here. To differentiate means to find the derivative. The act of differentiating is called differentiation. This is a noun here. Differentiation explains that you are doing the act of finding the derivative. And if a function has a derivative, then we say that the function is differentiable. This is an adjective. So we got a couple verbs in here, a couple of, got an adjective, got some nouns and such. All this has to do with the idea of finding the derivative of a function. This is a pretty important concept because, as I've mentioned on more than one occasion, one of the major branches of calculus is differential calculus, or being able to use the derivative. Now, notation. I showed you f prime here, and you could write f prime of x, that means the derivative, but you can also use dy over dx. Now, it's not a ratio, it's just an expression, which kind of means the derivative of y with respect to x. Or you can write d over dx times f of x. This is not really times, it's just saying you're finding the derivative of this expression with respect to x. Really kind of old school notation, as far as textbooks are concerned, is this notation with a capital D being the idea of finding the derivative of y with respect to x. These two are the ones that you use most often. All right, so dy dx is equal to the limit as delta x. Let's move this up a little bit so you can see it, hopefully. Well, if it won't slide on me. Dy dx is equal to the limit as delta x goes to 0 of the difference of the y values over the difference of the x values. That's the difference quotient function, and we write it as f prime of x. These are exactly the same thing. They mean the same thing, just slightly different notation. Let's find some derivatives. Okay, mark the date down. Your first derivative. Okay, very important time in your life. Let's find the derivative of fx equals x squared plus 3x. Well, we have to use the definition. The definition, I'm going to write it up here, is the limit as delta x goes to 0 of the difference quotient x plus delta x, f of x plus delta x minus f of x, all over delta x. All right. So now I'm going to take the limit as delta x goes to 0 of f of x plus delta x. That quantity means I'm plugging x plus delta x in here and here. So I have x plus delta x squared plus 3 times x plus delta x minus f of x, that's all this, so in parentheses x squared plus 3x, and that's all over delta x. So again, lots of algebra here. So this is the limit as delta x goes to 0. This would be x squared plus 2x times delta x plus delta x squared. I would suggest that if you have something times it, or if you're raising it to a power, put delta x in parentheses so to avoid some confusion. And that's this part right here. Here I distribute, so that'd be plus 3x plus 3 times delta x. And then here I have to distribute because it's a subtraction sign. So that's minus x to the second power minus 3x. And that's all over, yikes, delta x. Now, especially on these little polynomial guys, when you get to this point and you start to simplify, everything should cancel in the numerator that doesn't have a factor of delta x. Because otherwise, you're not going to be able to cancel that delta x in the denominator. So as you can see, I have an x squared here, I have a minus x squared. I have a 3x here, I have a minus 3x. And it gives me the limit. Don't forget to write this limit down because I'm still evaluating. 2x times delta x plus delta x squared plus 3 times delta x, and that's all over delta x. Notice that every term in the numerator has a factor of delta x because now I am going to factor that out. So I have the limit as delta x goes to 0, factor out that delta x, and that would leave me 2x plus delta x plus 3 all over delta x. Now you can see why we did all this. Can't find the limit as long as there's a factor of delta x in both the numerator and denominator because it would give me an indeterminate form. And I would have the limit as delta x goes to 0 of 2x plus delta x plus 3. Well, as delta x goes to 0, this is the only thing that's affected. This is going to go to 0, so this is going to go to 2x plus 3. So it says find the derivative. F prime of x is 2x plus 3. A lot of work there, and that was a fairly simple polynomial. Some of these problems can take a little bit of work. I'm going to do 2 more examples just to show you, because these are all kind of traditional looking types of problems that you might have to find the derivative. And again, this is only if you're finding the derivative using the definition. Later in the chapter, we'll have some differentiation rules that are going to speed this process up quite a bit. All right, so in this case here, I have y equals 2 over t. So that's going to give me the limit. Now notice here my independent variable is t, so I'm going to write delta t goes to 0 of, well, this is where we would have f of x plus delta x, so it would be f of, we would have f of x plus delta x, so this would be like f of t plus delta t, but it's not really written in that function notation. So I'm going to write 2 over t plus delta t minus f of x, or in this case, minus 2 over t over delta t. Here we go. This is fun. Now this time, again, if you try to evaluate this with direct substitution, you're going to get 0 over 0. So we have to do some algebra and kind of finagle this a bit. I'm going to get rid of the fractions within the fraction by multiplying top and bottom by my least common denominator. So I'm going to multiply top and bottom by t times the quantity t plus delta t. Top and bottom. Alright, so up top, I'm going to have to distribute. I get the limit as delta t goes to 0 of, now if I multiply all this times this, these are going to cancel, and I just have 2t. Minus, if I multiply this times this, the t's are going to cancel, and I have 2 times this quantity. So minus 2 times the quantity t plus delta t. On the bottom, nothing cancels. I have delta t times t plus delta t. I'm just going to write it all out. Here, I'll put the t first, times delta t times t plus delta t. Probably best to make your lowercase letter t's with a curved bottom so it doesn't look like a plus sign there. So if I distribute up top, I get the limit as delta t goes to 0 of 2t minus 2t minus 2 times delta t. Look at how all that stuff without the delta t's are going to cancel out up there. So I have t times delta t times t plus delta t. Oof. Sounds like I'm talking another language here. So I have the limit as delta t goes to 0. These are going to cancel. I get negative 2 times delta t all over t times delta t, the factor, and then times the quantity of t plus delta t. Whew. These are going to cancel. Yikes. So this is going to give me the limit as delta t goes to 0 of negative 2 on top, and on the bottom I have t times t plus delta t. Now my numerator is not affected by the is not affected by the limit. It's a constant. It's negative 2. But if this is going to go to 0, then t plus delta t, t plus something going to 0, it's just going to go to t. So t times t, I'm going to end up with negative 2 all over t squared. And this would be y prime. That's another way. If it doesn't have function notation, you can just put the prime next to the y. That would be your derivative right there. Okay? All right, now we got to try one with a radical, and I took the simplest one I could think of, and that's g of x equals the square root of x. So I'm going to take the limit as delta x goes to 0 of g of x plus delta x. I'll go ahead and write it out rather than rolling it back down here, times g of x all over delta x. I'll be doing this in my sleep. This is the limit as delta x goes to 0 of, this would be the square root of x plus delta x minus g of x is the square root of x all over delta x. Well, we did one a little bit like this in the previous chapter when we were trying to evaluate a limit. I'm going to multiply top and bottom by the conjugate, because if I use direct substitution, I get 0 over 0. So top and bottom by the conjugate, which would be the square root of x plus delta x plus the square root of x, the square root of x plus delta x plus the square root of x, and this would give me, you see that? Yeah, I think you can see that okay. The limit, what a mess this is going to be. The limit as delta x goes to 0. Now here I'm going to do FOIL, but the outer and the inner are going to cancel because these are conjugates. And I just get this times this, which is x plus delta x, minus this times this, which is just x, all over, what a mess down here, I have delta x times the quantity of the square root of x plus delta x plus the square root of x. The x's cancel, which is good. I get the limit as delta x goes to 0 of delta x all over the quantity, or delta x times the quantity of the square root, better make that a little bit longer, x plus delta x plus the square root of x. Cancel out as a factor of 1. I get the limit as delta x goes to 0 of 1 all over, looks like the square root of x plus delta x plus the square root of x. Well, as delta x goes to 0, this is going to go to 0. X plus 0 is x. This is going to be the square root of x plus the square root of x. This is going to be 1 over 2 square roots of x. Now I know you can rationalize the denominator, but I'm not very worried about that right now. I'm going to say that my derivative g prime of x is equal to 1 over 2 times the square root of x. Drink that in. A lot of algebra there, and as I mentioned before, we're going to look at other sections that are going to give us some differentiation formulas that are going to make this go a little bit faster, but this is how you find the derivative by definition. Now there's an alternate form of the definition for finding the derivative of a function, and that is that f prime of x is equal to the limit as t goes to x of f of t minus f of x over t minus x. It's still the slope, and it's still the slope of the secant line. It's just that t is approaching x, so our secant line becomes closer and closer and closer to the tangent line. This also, this particular form also kind of ties in, or kind of brings together the idea of how differentiability and continuity kind of go hand in hand here. So let's scoot this over here, and let's look to see what we can do here. At a point c f of c, f prime of c is equal to the limit as x goes to c of f of x minus f of c all over x minus c. If we look at the limit from the left and the limit from the right, okay, we can say that the function's differentiable on the closed interval, and if it's differentiable on the open interval, and the derivative from the and if the derivative from the right at a and the derivative from the left at b both exist. So if all this is kind of like what we were talking about with continuity. How continuity on a closed interval, we'd have to look at the endpoints individually. Well, we do the same thing here with differentiability. If a function is not continuous at c, or on dry land, it is not differentiable at x equals c as well. All right, for example, good old greatest integer function, f of x is equal to the greatest integer of x at x equals c. Well, if we look at the derivative here from the left side, from the right side we get 0, but from the left side we get infinity. So what does that mean? What does that mean? Well, that means that the derivative doesn't exist at that endpoint. Okay, as x goes to 0, that doesn't exist. Now, in that doesn't look quite right. As x approaches 0, yeah, because what's happening is x approaches 0 from the left. This is going to be -1. This is going to go to 0. Negative divided by negative is positive infinity. Yep, I got it. Didn't look right for a second, but it is. So continuity does not imply differentiability. For example, f of x is equal to the absolute value of x at x equals 0. If I was to look at the graph, kind of sloppy, but there's the graph of f of x equals the absolute value of x. Do you notice here you've got a point, or like a vertex, or a cusp at x equals 0? Well, there's no way that the derivative exists because there's no unique tangent line. The derivative and the tangent line go hand in hand. So you'd have to be careful here. And over on this guy here, we have continuity. We have g of x is equal to the cube root of x. You can plug in any value you want. Now what happens here is you get something graphically that looks kind of like this, where we have, and I mentioned this before, we have something that's referred to as a point of inflection, where it changes from kind of curved upward to curved downward. At x equals 0, we would have a tangent line that would be vertical. So the derivative doesn't exist there. So continuity does not guarantee differentiability, but the other way around, which is where I was leading to, is that differentiability always implies continuity. If f is differentiable at x equals c, then f is continuous at x equals c. All right? Differentiability implies continuity, not necessarily the other way around. All right. That finishes up section 2.1 here in chapter 2.